We all comfy with why it's exponential? So Miles says yes. Shadidra, can you tell us how we know that these are exponential functions up here? So be careful. I don't see a line anywhere up there. So remember, lines, linear, have a constant additive rate of change. These do not, right? Those are not linear functions. You can say curves. It's all, specifically, what kind of curve is that? An exponential curve. There we go. But, sorry, let me restate my question. So, Shadidra, how do I know from the equation that this is exponential? In the what? Think about the name. Exponential. Where's that x? That's why we call it an exponential, right? Remember, your variable's in that exponent. In any way, we call it an exponential. All right? So this is a straightforward exponential function, which means it has a constant multiplicative rate of change. And so one of these should be really, really, really straightforward. Which of these functions is this graph right here? Why do you think it is j of x? So what's below 1? So be careful again with our language. J of x is not below 1. Because like right here, all of this for j of x is well above the number 1, right? What about j of x is below 1? The constant factor, the base, you can say either of those things, right? That base, that constant factor is less than 1. So we're constantly making that number smaller. Literally what we're doing is we're multiplying by 3, but then dividing by 5. If you divide by a bigger number, that number gets smaller. We all comfy with j of x there? So what do we call that direction of the curve? An exponential decay, right? So it's a decay, it's decreasing. But now some of us I think might be having a little bit more trouble on these, and so I'm not going to go into as much detail right away on these, but which one do we think this one is? This is, which one? The 3 to the x? So g of x? Alright, so I'm hearing g of x here. Okay, what about this one right here in the middle? F of x is a claim. And this one here would then be k of x. So someone other than Jaden, Miles, Landon, I heard someone else just say, make those claims. Can anyone add on to justifying this or push back on those answers? No, I just said except for you because you're the one who told us these answers. I need others to either justify saying, yes, I agree, giving extra information, or push back on that information. Sandra, what about you? You haven't said anything yet, right? What do you think with those three? You agree, disagree?
I agree.
You agree? What's your justification for that?
Can I get up and just show it or no?
Say it a little bit louder.
Can I just get up and like show it or no?
100%. Come on with it. I would love that. I just don't want to force you to do that.
I'll put this one in.
Okay, explain why that's important, because I don't know if y'all noticed this or thought about this before, but I was thinking that that was going to be the detail I was going to have to explain to everybody. So I'm really glad you're noticing that. So what are you noticing right there?
Like, if x equals to 1, then 3 times 1 is 3.
3 times 1 is 3. Right here, what is my output? What's my f of x? Right here at the y-intercept? 1. And what's 1 times 3? 3. Notice that's not a slope, but that is a constant factor. We've got 0, 1, and then notice it does go 2 squares, so that's 1 comma 3. Constantly multiplying by what? 3. Thank you, Xander. That's fantastic, right? So that's pretty strong evidence for g of x being this function right here. Whee! All right, so why then is this one right here, f of x? Same reasoning, right? When I look right here, what is this point? 1 comma 2. So we multiplied by 2. We're going to keep multiplying by 2. Notice it goes from 1, 2 to 2, 4. Constantly multiplying the output by 2. So that means k of x has to be this blue one here. And let's at least investigate Does that look like it could be about 1 comma 1.3? Sure, it's between 1 and 1.5, isn't it? One final thing I want you to pay attention to and I want you to notice is this. What's causing this to get steeper and steeper? What's increasing? The base. And so that's what I was thinking we would notice right away. And that's totally fine that we didn't, but always keep in mind that if the base is getting bigger, you're multiplying by a larger number, right? So what's it going to do? It's going to increase or grow more quickly, right? So please notice like all those ideas going together, but at the end of the day, a function is a set of what two things? Inputs and outputs. For every single one of these, you could have made a quick table. Negative, well, let's go 0, 1. So to go backwards, I'm going to divide by 3. And to go forwards, I'm going to multiply by 3. 2, 9. F of x here. And notice this is helping us review a little bit of those old concepts if you struggled with it. If I substitute 0 in, 2 to the 0 is 1. What's 2 to the first? 2. What's 2 to the second? Notice we're just constantly multiplying by 2. And that rain is coming on in. A function, inputs mapping to outputs. That's it at the end of the day. Questions, comments, concerns about this exponential growth versus decay? So please write the details you need to your future forgetful self about those growths, those decays, the idea of inputs and outputs, maybe making a table, whatever you need to do. While you do that, I'm glad I made the note to myself to finish passing back the Unit 5 test. Okay. So please remember, you can come in during advisory, before school, some days after school. We can sit down and talk about some of these things. I definitely gave feedback because there's a lot of us that had really good starts to our understanding, but we're missing some key details. I did update proficiency scales with these things, so make sure we use this as a learning opportunity. I get it. I know that at some point a grade has to go on a transcript, but learning is the priority. And so make sure you learn out of this, and you're going to be more than fine. You still have a week to show me proficiency with anything you have not up to this point. And so with that, let's figure out a way to show proficiency with things you did not originally. And if you did not get it back just now, that means you got it back yesterday. Okay. And I will say the goal is also to test Friday or the first half of Monday so that we can look at old tests, we can review things like that to prepare for the final if you need to take the final. But if you don't need to take the final, once again, the grade isn't what really matters. It's the learning, and the grade comes out of that learning. So let's learn over those last couple of days to prepare for, or to show extra proficiency, earn that higher grade in the middle of class. Okay. So Unit 7, Logarithmic Functions Agenda. So we already did the Lesson 1. We're going to wrap up, actually we just wrapped up the Lesson 2. And now we're getting into Lesson 3, which is all about what a logarithm is as a function and as an operation. Hopefully we should finish this today so that we can actually start on the next part of logarithms, which is actually just building on it a little bit more and then actually solving logarithmic equations and exponential equations. Thankfully, you've actually started doing that already within that last unit on inverses. So not going to be adding a ton of new stuff in. Some of this I'm going to be doing as direct instruction to make sure we can get to that second half. But right now what we are focused on is we actually already did all those. So actually, no. So we're going to get back to this idea of what a logarithm is. But that's the only foundational piece of the lesson we're looking at. The rest of this we should do. We are about to get a little bit of practice with identifying the features, because we haven't done it with a logarithmic function, but it doesn't change a ton from exponential. Are there any of these foundation pieces besides explaining what a logarithm is or identifying the features that you need to ask a question about? Or you want to ask a question about? Doesn't mean that you haven't mastered it, but maybe you just want to clarify something, confirm that you know what it is. Going once, going twice. Sold. Thank you. Grab a seat at the 10s, but we'll have you work with, let's say the 9s today, okay? 10s are the only one that just have a space. Yes, ma'am. You need the Unit 7 proficiency scale? Let's see if I have one printed out right here. Yeah. It says Unit 6, but it's logarithms, that's Unit 7. Okay? Yeah. All right. So what we're about to get into more is, honestly, everything vocabulary-wise from the target. Yep. We're not going to get into properties of logarithms today, I will say that. Asymptote, we talked about it yesterday, I'm going to recap it in just a second. We are going to be looking at graphing basic logarithmic functions, rewriting exponential equations as logarithmic and vice versa, and evaluating logarithms with integer exponents, and then estimating with rational exponents. So we're essentially going to be doing this entire little section, solving exponential equations and logarithmic equations is the next piece. So we're going to be working lesson 3 on all those concepts. We will continue practicing those within the next set though. All right. So here's actually a huge little recap that we're going to be using. So right here, this is page 126. Please turn to that page from the book. Page 126. So notice we have the function f of x. What type of function is f of x? Ooh, nice. I wasn't even thinking about that. But is f of x a one-to-one function? Yes. Right? Passes that horizontal and vertical line test, meaning its inverse will also be a function. But, I mean, like, specifically, what type of function? Exponential. How do we know it's an exponential? There's 3 ways. Not just a curve, because remember, this is not exponential, right? But that's got a curve. Okay, what about the exponent? The exponent is a variable, is the x, right? That's one reason that we know it's exponential. Which form or which mathematical representation are you referring to? So bringing those vocabulary terms back in. Algebraic. Remember we talked about equations, expressions, inequalities. That's algebra. Algebraic. Good with that, Megan? Okay. So algebraic. Now, let's go back though to what Landon was talking about. He was referring to a curve. What type of curve? Exponential curve. Which mathematical representation is that? Graph, right? Be careful with just a curve, right? Like, there are infinitely many curves out there. There's only one exponential curve. And we want to say exponential curve for that graphical. All right, what's the last reason I know f of x is exponential? The rate of change. What's happening in that table for that rate of change? Multiplying by 2, right? That's that constant factor times 2. Constant repeated multiplication. So we know there's an exponential function from the very beginning. We got it algebraically, we got it tabularly, we got it graphically. We want to see all those connections to master these ideas. And so, Crystalline, read this statement out for us as a class. What is this saying?
I know what it is. I don't know how to see it.
What do you think it
The
is?
transverse of x of x? X of f of x?
So we got some correct ideas in there. Now, not transverse. What are you referring to? Anyone know where she's trying to get out there? Transpose, right? What's transposing? Not f of x. When we say transposing, we're specifically referring to one part of that function, inputs and outputs, right? So what you're trying to refer to is transposing inputs and outputs. There we go. But Davis, when we say the inputs and outputs are transposing, what are we referring to? Malia, let's put that up, please. What are we referring to when we say the inputs and outputs are transposing?
The X and the 1.
We just had a whole unit on this. Makes me nervous. I haven't looked at those tests yet, but y'all making me nervous. Like, inputs and outputs transpose for what type of function? The inverse function. How do we read this statement? We're looking for the inverse of f of x. So, the inputs and outputs transposing, we can actually see that in this table, right? Negative 3 1/8 became 1/8 negative 3. But we need to recognize and refer to, when we read that out, that is the inverse of f of x, meaning the inputs and outputs transposed, right? What else does that mean? Like, when I look at this graph here, what do I want to notice about the relationship of f of x and the inverse of f of x? Say it louder. Reflection across what? Okay, so I just want to recap all these ideas. Inverse functions, that's a reflection across that line y equals x. I would probably draw that in to show these things, right? 1, 2 became 2, 1. 0, 1 became 1, 0, etc., right? Like, we see that inverse of f of x, the reflection across y equals x, the inputs and outputs transposed, all these are really, really, really important ideas. Now, there's one final thing I want to point out. I want you to look at the table. I want you to look at the table for the inverse of f of x. What's the rate of change for that table? Constant additive? Well, that would make it a linear function, wouldn't it? Is that a linear function? Guys, is this a linear function? Look at the graph. Is it linear?
Yes.
You're forgetting, I cannot just look at the outputs. What else do I need to look at? What's happening with my inputs? It's constantly multiplying by 2. Or it might make more sense to put it here. So notice, is this a linear function? Heck no. Guys, what is the inverse of an exponential? You know this. Say it louder. This is a logarithmic function, right? My inputs and my outputs transposed, my rates of change switched, that constant multiplicative for my output is now my constant multiplicative for the input. That's how I know it's an inverse function. So, because we've already tackled it, the textbook wouldn't have expected us to tackle this yet, but because we already tackled it, I know that the inverse of f of x is a what type of function? Logarithm. Now, is that the correct logarithm?
No.
Why not? Okay. The base has to be what? 2. What is the base of this? 10. Which, does anyone remember what we call a base 10 logarithm? Common log, right? What'd you say? What did you call it? Okay. It's called a common logarithm. When there's no base written, it's a log base 10. So just keep that in mind. We're going to look at that more later. That's called the common log. but we need a log base 2 of x. So we need a base 2 logarithm to go with a base 2 exponential. Alright? So please notice these things. The last thing before I release you to get to vertical surfaces and look at things, I want you to think about this. Nope, let's make my life easy. What type of function are we looking at here? What type of function are we looking at right here? If I'm telling you that this is the inverse of f of x, what do you think I'm looking at? This one? Linear? Why do you think it's linear?
Adding by 1.
Yeah. Anybody have any other ideas that we could push back or add on to? So this is an inverse function, but remember, just in general, I need to look at both the inputs and the outputs. Even if I didn't put inverse of f of x, look at the other side. It's not quadratic. It's a square root function. What's the square root of 0? Square root of 1. Square root of 4. Okay? This is the square root function. Remember, when it was linear additive on the right-hand side, it was quadratic. Now that it's on the input side, though, it's the inverse of a quadratic, which is a square root. Okay? So I just want to make a connection there. I want you to notice that those rates of change that we studied in the past are still super valid with inverse functions, but if it's on the input side, it's not a quadratic, it's a square root. If it had a quadratic additive rate of change, on the input side, it's not cubic, it's a cube root. So I want you to make a connection between those inputs and outputs, okay? What are your questions before we continue? I will point out, this is not something I'm testing you on, but that is to build a deeper understanding. Questions, comments? It might be for future classes, but did not put this on the proficiency scale. So here's what I want you to do, okay? We're going to complete the table identifying these key characteristics of each function, okay? And so we have the f of x and we have the inverse of f of x. This is going to help us practice some more important ideas. I do not want you to worry about intervals of increase and decrease. I do want you to do domain, range, y-intercept, asymptote in behavior. Okay? So I want you to identify those features on your vertical surfaces with your small groups. We're going to take 7 minutes to identify every single one of those features. Talk about it with each other, especially if you are struggling with domain and range. Especially if you're struggling with intercepts. Because I saw quite a few already who were struggling with domain and range yesterday. We need to make sure we ask and understand. Yes, ma'am.
This range is
Have you talked to your group about it yet? Okay, talk to your group about it, then I'll answer your question if you still don't understand. Also, we can get our notes out from yesterday as well. That might be helpful. Start up here, and I'm actually going to go backwards a slide so that we can clearly see this. Now, 2 things I need to remind you about, and I need you to keep in mind at all times. Oh, sorry for whoever this is. We'll use other people's stuff. But I need you to remember, when we say domain, Shadidra, what do I mean by domain? The x values. So what direction are we thinking if we're talking about domain? That's left and right. Left and right. And I need a minimum and I need a maximum. Make sure that if you are doing domain and range, you talk about a minimum and a maximum. We good with that?
Yes.
Comfy? Alright. Couple of connections I'm going to make. I need you to pay attention to this, right? So a lot of us around the room, we said that domain is negative infinity to infinity. Does it ever quit going left? Does it ever quit going right? Never does, right? So domain and range, or domain is negative infinity to infinity. So without looking at my graph, do I know the domain or the range for the inverse of f of x?
Yes.
Which one? So we just identified the domain of f of x, right, is negative infinity to infinity. So based on that, do I know the domain or the range for my inverse of f of x? I know the range. Why? Why is that now my range for the inverse of f of x? Okay, so reflection across y equals x is part of it. Why else? So what's transposing? The inputs and outputs. So what was my inputs, the x, the domain has become my outputs, my range. That feature has switched, right? And so, Laney, can you actually just go ahead and bring over here? So for my f of x, the range, right? What is the lowest y value for that exponential? What's the lowest y value, the range?
Oh, 0.
0. Does it ever go below 0? No. Why do we not put a bracket this time, though? Why do we put a parenthesis there? It what? It never actually gets to the 0, right? It never gets to the x-axis. We never actually have the 0, so we put a parenthesis there, not a bracket. Boom, right? It's approaching, but never quite gets to 0. It gets really, 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 really close to the point that it's essentially the same, but it's not the same. It's wild stuff. But if that's my range for f of x, what is that going to become for my inverse of f of x? Domain. Notice, once again, it's approaching now the y-axis, but it never quite gets there. Boom. Okay? And so I'm not going to spend a ton of time for y-intercept and x-intercept, but I do want to point out, like I was talking about this with the 9s earlier, and I said, hey, you have your y-intercept for f of x and inverse of f of x, and without even looking at the graph, I knew this was the x-intercept for f of x. How? The inverse, right? So what's important about that? What was my
Input,
well, input has become the,
output.
actually this is output. So this is my input. Nope, nope. X-intercept, there we go. But this was my input. It has become my output. And this input became the output. I say it that way because I'm looking at the x, the 1. I mean, it's still the same thing. But a big idea is that those features switch. Because those inputs and outputs transpose, my features switch. Keep that in mind. Because those inputs and outputs transpose, the features switch. And I know a lot of us struggle with asymptotes. That's fine. I get it. But an asymptote is quite literally just a line or a function, or a line or a curve that a function approaches. And so I kind of made this example or something similar for a couple of groups. Whee! Okay? So there's a curve. What type of curve is this blue one right here? Exponential. And I want us to notice, if I drew it perfectly, that curve is approaching this line. But what is it? It's -3, but what's -3? So we want to notice, and this is something I did with one group, and I didn't do it with every group, but if you look at any point on this line, it doesn't matter which point you look at, the output, or the y, is -3, right? So it's just a line or a curve that function is approaching. And so I noticed this group over here, the aces, y'all made the note that it was approaching the x-axis, right? But what would the equation for the x-axis be? Y equals 0. On that x-axis, the output, the y, is always 0. Which means for my inverse of f of x, what equation do we now get? X equals 0 is my asymptote. And now this is what I really want you to pay attention to, because y'all are finding this off the graph, and that's great. But I also want you to notice, what was my lowest y value?
0.
My asymptote is y equals 0.
0.
Now, please hear me. You're going to get into something called rational functions, and that's not going to be the case there every time. Actually, most times it won't. But there is still a connection there. But for exponentials, it is going to hold that asymptote is what is going to impact your range. Or with the inverse of f of x, what was my lowest value for the domain? 0 in the x. right? So I just want you to see that connection between the domain and the range and the asymptotes, right? So it's approaching that curve or that line, but it's not quite getting there. Okay. The other final detail I want to point out is this. The rest of this is great, but I just want you to notice this right here. On the left-hand side, let me write actually a little bit bigger. On the left-hand side, as x goes towards negative infinity. So as we're going towards an infinity, right? What's the y going towards? Oh, and my asymptote is y equals 0. Right? It's the line or curve that a function approaches at an infinity. Over here, this left-hand side, again, those inputs and outputs transpose, but now it's as x goes to 0, y goes towards negative infinity. And what was the asymptote for this one? X equals 0. Notice, there's my asymptote within the end behavior. So use your end behavior to help inform your asymptotes. Okay, let me say that one more time, and I want you to take the time to write the notes you need to about these features, ask some questions, but use the end behavior to inform your asymptotes. They are very heavily connected. And I will say this, domain and range don't always hold perfectly with asymptotes, but end behavior does. Because it's at some infinity. So your end behavior really should inform your asymptotes. Your end behavior really should inform your asymptotes. So take a few minutes, write notes, ask the questions you need to ask about any of these features, and then we'll start back on the next couple pages in let's say 3 minutes. So this is some of the language things. Oh, Landon, what did you do? He didn't break it, but... Okay. Alright, so this is page 127 out of the textbook. I want you to pay attention to the language. A lot of this language is actually really, not, yes, it's important, but it's exactly what we talked about, okay? And so at the end of the day, okay, so before we get too far looking what the textbook is, I want to establish this more conceptually than what the textbook has. If my input is 0, what's my output for 2 to the x? Ladies and gentlemen. If I'm looking at y equals 2 to the x, my input is 0, what's my output? 2.
1.
Thank you. 2 to the 0 is 1. So when I look at a logarithm, what's my input going to be for x? 1. And that's my output is going to be 0. Okay? If my input is 1 here, my output is going to be 2. And so here my input would be 2, and my output would be 1. Here I have an input of 2, my output is 4. And here, 4 maps to 2. And I want you to think about this, because it can keep going. What numbers are we essentially spitting out when we take a logarithm? What is being asked in a logarithm? So like what we're saying, let me clarify this. So this is log base 2 of 1 is equal to 0. Log base 2 of 2 is equal to 1. Log base 2 of 4 is equal to 2. If I continue this, it would be 8 and 3. So log base 2 of 8 is 3. So when we evaluate a logarithm, I want to draw your eyes to this. This is the connection. What is a logarithm? What are the outputs of a logarithm, essentially?
You're starting x.
So it is a starting x value, but I want you to think about what that x value is every single time and say what? Not just an input. Think about the type of function. Think about the type of function. What's the 0, the 1, the 2, the 3 for the original function? Say it louder, Kristen. It's an exponent. And what is the output then for the logarithm? Say it louder. It's an exponent. I need you to clearly hear me on this because all the time students stress about logarithms. I cannot tell you how many times I've worked with Mu Alpha Theta, the Math Honor Society, or math team, and they're like, oh, I just really didn't learn what a logarithm is. Like, we did it, but it doesn't make sense fully. Guys, at the end of the day, a logarithm is an exponent. That's it. So when I ask you, or ask somebody, log base 3 of 27, I want to know what, I'm trying to find a what again? Starts with an E. An exponent. I want to know what exponent goes on 3 to give me what? Well, what exponent is that?
No.
Let's type 3 to the 9th into the calculator.
Huh?
Yeah, 3, so what? What did it be?
Maybe 3.
If you have an exponent of what? 3. Let's try it. What is 3 to the 3rd?
No. 27.
3 to the 3rd is 27. So what's my exponent? 3. Guys, if I am asking you, or if anyone is ever asking you to take a logarithm of a number, 1, it's the inverse of a what? Exponential. Okay, so logarithms are the inverses of exponentials, and so my output is simply the what? Well, the original input, which is an exponent, right? Logarithms are the inverse of exponentials. So the output is simply an exponent. That's it. The output is simply an exponent. So what I want you to do really quickly, if you're already done taking those notes, I understand if you're not, but I want you, if you're done with your notes, to type in log base 5 of 83 and tell me what that is. So type that into the calculator, log base 5 of 83.
2.74. A decimal.
It's a decimal?
Uh-huh.
Okay. Yeah, log base 5 of 83, 2.7. I think there might be even more decimal after. 4.
5, 5, 8.
And I will point this out, actually, if you just type that in, I want you to hit the up arrow, highlight that number, and then hit enter. Why did I ask you to do that? It's showing more numbers, right? Does anyone know what kind of number this might be?
Nope.
It's a classification system. Like, is this an integer, a whole number, a rational number, imaginary? It's what?
Irrational.
It's irrational, right? Like, these are going to be irrational numbers. Okay, so we want to notice these are in fact irrational numbers, but I want us to understand what this really, really means. So first off, I want us to think, does this number even make sense?
No.
Well, what's 5 squared? 25. What's 5 cubed?
75.
Calculators, guys. 125.
125.
What I would point out is 5 cubed is just 25 times 5. And what's 20 times 5? 100. And what's 5 times 5? 25. So 125. That's where that's coming from. So I want you to look at this again. I want you to think about it. Does this make sense in this context? What is a logarithm really?
An exponent.
An exponent, thank you, right? And an exponent of
Oh.
2 gives me 25. An exponent of 3 gives me... So would an exponent of 2.75 maybe give me 83 somewhere in between there?
Yeah.
Yeah. Okay, why don't we type in 5 to 2.74558. By the way, one thing I would point out is, don't forget, hey, pause for a second, because I want you to use this for the ACT and other things like that. You can type in 5 raised to, notice I can go up and highlight that number, hit enter, and it brings it down into the exponent.
83.
83.
83.
And so, two things to notice about this, okay?
That's all.
Okay. Are you being nice and respectful?
Yeah.
Because you ain't trying hard enough in that realm either.
I was.
Uh-huh.
Making sure she get home.
Okay, so what I need us to notice is the logarithm and the exponential, they undid each other. What was my input by the end was also my output. They cancel each other out, but also, what is a logarithm at the end of the day? It is simply an exponent. I need you to clearly understand this idea. At the end of the day, a logarithm is an exponent. Which is why in the textbook, what does it say that logarithm is equal to? Right there. What does it say? It says it's an exponent, right? The logarithm of a number is the exponent to which the given base must be raised in order to produce that value. The only other thing I want us to pay attention to in this statement down here, actually it's two things. One, what do we call this number down here? Base. And what do we call this number right here? You didn't even look at what I'm pointing at. It's called an argument. For the longest time I was like, oh, the argument is just something I got to memorize. What I found out literally last year, so please understand, like I'm always growing as a mathematician, as a learner, as a teacher. In math, the word argument just means input. In math, argument literally just means input. That's it. So, when we say this, right, when we say the argument, that's the input, which was the output of the exponential. Okay. And please hear me on how I read this. We read it as log base 2 of 8 equals 3. But focus on the left-hand side, because a lot of students misread this. Log base 2 of 8. That is making the 8 my input. We read that as log base 2 of 8. And that's going to hold for any type of logarithm you ever do. So how would I read this statement right here? Of 1/9. Anyone have an idea what that logarithm might be equal to without using a calculator?
No.
Now, say that one more time. Maybe a negative number. Because what is a logarithm again at the end of the day? An exponent, right? And what type of exponent causes us to divide? Well, not less than 1. A negative. The number you said originally. Remember, what is, let's start here. 5 to the 0, what is that? 1. What is 5 to the first? What is 5 to the second? So so I'm multiplying by 5 going this way. So if I go backwards, what's 5 to the negative 1? 1 divided by 1/5. What's 5 to the negative 2? 1 divided by 25, or 5 times 5, 2 divided by 2 5s. When we talk about a negative exponent, it just means division. So Miles is right, like maybe a negative. Do not forget, a negative exponent is what causes division. So, negative what? Any guesses?
2.
Yeah. Isn't 3 squared 9? 3 squared is 9, so 3 to the negative 2 would be 1 divided by 9. That's it. So Jaden, at the end of the day, what's a logarithm? Do not forget that. Please do not ever go to a future math class and be like, I don't really know what a logarithm is. It's an exponent. Like there's other properties, there's other things we can do with it, but a logarithm is an exponent. Please do not forget that. A logarithm is just an exponent. Students struggle with it all the time, and it doesn't have to be a scary thing. In fact, it shouldn't be. It's just an exponent. I'm just going to quickly show a couple of these, but I want us to get some practice with it. So, right here, I just want to point out, 16, does that equal 4 squared? Is that a true statement?
Yes.
So then I'm going to do log, and why is it base 4 here?
Where?
So like right next to 16 equals 4 squared, it says log base 4. Why is it base 4 for that logarithm?
Or log just
That's the base of the exponential, isn't it?
Yeah.
We use the word base for both because they're both going to have the same base. What was my output is now my input, also called an argument, right? That output of 16 became the argument for the logarithm, and that is simply equal to 2, because that's my exponent. So without looking over to the right-hand side, let's think about how we're going to write this statement as a logarithm. So how are we going to write this as a logarithm? Log base what?
10.
Did I need to write that base 10, by the way?
No.
No, what are we going to call it if it's not written there and it's understood to be base 10? Common log. So notice, you can read it as log base 10, or just say the common log of 1,000 is equal to 3. A logarithm is an exponent. So whatever the exponent is, that's what the logarithm is equal to. Because it's tough to memorize what goes where, but if you understand that a logarithm is an exponent, it's really easy to keep it straight. So when I say log base 16 of 32 is equal to 1.25, and if I want to write that as an exponential, what am I going to write first as the base for that exponential? For log base 16 of 32?
Oh, that's 16. No, that's 16.
Base 16. The base is the base. What's going to come next in that exponential? So the... What is that 1.25? That is the...
Exponent.
Thank you. The exponent is 1.25. And what is 16 to the 1.25 apparently equal? 32. So it's understanding, at the end of the day, what's a logarithm? An exponent. So what is your output? What is your exponent here is the exponent here. What the base is here is the base here. That's it. That's logarithms. That's evaluating logarithms in a nutshell. So, a couple of things I want to talk about here. So this is what, page 128. We're going to look at a couple of things here. It's a super generalized exponential equation. In this exponential equation, f of x equals b raised to the x. Actually, I'll just call this y to make things simpler. Notice it's asking about restrictions. Are there any restrictions? So like if I were to graph b to the x and think about that function, are there any restrictions for x? Anything that that input cannot be? So anyone know, can I do b to the 0? What's b to the 0? 1. So I can have an input of 0, that's okay.
Can you have a negative?
That's a great question. Could I do maybe, I don't know, b to the negative 3? What would that give me? So 1 divided by, and it's going to be awkward, but b cubed, right? That's what it would be. So can I have a negative exponent? Yes. So are there any restrictions on x? So remember, thinking about our exponential function, what was the domain of all exponentials? The domain, the inputs was negative infinity to Positive infinity. So are there any restrictions on this x?
No.
So no restrictions on x. Okay, what about the base? Were there any restrictions on the base of an exponential?
No.
It cannot be what? You're close.
That's one. What?
It cannot be,
Zero.
so it can't be negative, right? It also cannot be 0. Were there any other restrictions? And it also cannot equal 1. So, in this exponential, remember b could not be less than or equal to 0. Notice less than or equal to, and I put a slash through it, the slash meaning not. So that just means b is not less than or equal to 0. And b does not equal 1. Why is that the case? Say it louder. It wouldn't be an exponential function, right? Like when I looked at that graph, if b was those values, was it an exponential function? No, Mr. Kinney. Thanks, guys. So, not an exponential with these bases. Notice that's just going back to the calculator. It would not be an exponential with those bases. What's up? Why would I feed dog? It's weird.
My socks got wet.
You don't necessarily need to wear socks with Crocs, do you?
We
Yeah,
know.
I would not put on socks when it's raining
Wait,
with Crocs.
Because it wasn't raining when I looked down.
Oh, okay.
It wasn't raining when I looked
Okay. Regardless, all right, from all that, y, are there any restrictions on what the y value can be, the output for an exponential?
down.
Are there any restrictions on what the y, the output can be for an exponential?
No,
You sure about that?
no,
Look at your graph.
yes. Yes. It can't be negative.
It cannot be negative, it also cannot be 0. Remember, the range was 0 to infinity? That was the range of an exponential. And I go through all of this because I need you to clearly understand that when we look at the book, what would be the logarithmic version of that equation? What would I have? I'll have a log,
Log, base b
base b,
equals, y
not of x.
of y.
Remember, what was my output is now my input
Log base
is equal to
x.
x. So what's going to be the restrictions on b for this logarithm? What can b not be? It cannot be 0. It can't be 1.
It can't be negative.
And it can't be negative. The same restrictions on the base and the exponential, those are the restrictions on the base and the logarithm. The restrictions on the base and the exponential are also the restrictions on the base and the logarithm. Anyone know what the restrictions on y are going to be for that logarithm? The same. So what's going to be the domain of a logarithm? Or the argument? 0 to
Infinity.
infinity. And what's going to be my outputs? Are there any restrictions on the outputs of a logarithm? Nah. I want to point this out. I need y'all to note this, and I'm going to give you a few minutes to write this down. But right here, remember when we looked at an exponential and we looked at a logarithm? How the domain, the inputs, was negative infinity to infinity for the exponential, but the range was only 0 to infinity? That's exactly what we're seeing over there. And now the logarithm, the only inputs we can have, the only argument we can have is 0 to infinity, but the range, the outputs can be anything. So if you understand an exponential, you understand a logarithm because it's just those features switching. I want to give you a minute or two to write whatever notes you need to down about those restrictions, but please make a clear connection between those features in the exponential and the logarithm. Make sure that it's clear that what we're doing is the base stays the same, and inputs and outputs what? Say what?
Oh, transpose.
Thank you. Use that mathematical terminology. Right, that's it. The inputs and outputs transpose. That's it. Okay, so write down whatever you need to. Hey, you sleeping in my class? Wow, then. Can you stand up, move around a little bit, wake yourself up? You missed some important information. P.S. The textbook does this dumb thing with a triangle of power. Just think about a logarithm as an exponent. So unnecessary. There's a lot that I liked about the way the textbook does. The triangle of power is dumb.
I was gonna be able to use the calculator on it too.
For part of it. I need to see that you understand what a logarithm is. On these calculators, you can type in log base 2 of 8 and it's going to tell you 3. I want to see that you understand what a logarithm is. Dog, you typing that into the calculator, does that tell me you understand what a logarithm is?
No,
It tells you how to use logarithm.
you're not gonna have a calculator all your life.
Well, it's not just that, because here's the thing, and
I don't know.
a lot of teachers will hate on me for saying this, but I wholeheartedly believe this. At the end of the day, unless you're going into engineering or some STEM-related field, you don't need Algebra 2. But what you do need is the ability to think. I want to see that you can think with this information. So that's going to be the focus on my assessments. And I know you're like, well, Mr. Kinney, why are you expecting me to learn this? Well, one, I want you to learn how to think, and two, it's still my job to teach Algebra 2. I'm legitimately I'm petitioning the state of Alabama, or I'm going to start that process over Christmas break, to change the requirements from Algebra 2 to taking like a data science class or something else, but education moves slowly. Data science would be way more useful.
Why is that?
Huh?
Why is that?
So data science is this overlap between understanding statistical processes, a little bit of computer programming, and what's the other? Oh, and math. And so, but it's like all real world based, and it's all about literally understanding how to collect and analyze data and using technology for that. That's way more useful for most people's day-to-day life.
So you would teach it pretty much.
That's what my goal is, to eventually teach it wholeheartedly. One day when I'm hopefully teaching future math teachers at some university way in the future, my goal is to focus on data science as a whole, because it's way more useful. But until then, Algebra 2, I still love it, it's beautiful, it's just not everyone needs Algebra 2. Alright, so here's what I want you to do. Don't do the dumb triangles of power. I just want you to think about how you could use the information we have to figure out what these values of x are. So let's not go to vertical surfaces. I just want you to take a couple of minutes, talk with your group, figure out how can I rewrite these on page 128 or 129. I think it might be 129. No, not number 2 right there. Number 2 is 129. Okay? So I want you to think about how you could rewrite those equations to figure out what the value of x is. 129, at the top of 129. I want you to just talk with each other, figure out what x is in each of those, and how can you figure out what x is. You don't have to worry about the triangle of power, that's dumb. Just how are we going to figure out what x is?
feeling it.
Any guesses? Do you think the x is 10? Why do you think that x is 10? What is a logarithm? An exponent, right? So what you're telling me is 10 to the 10th is 1,000?
No, it's 3.
And then the exponent's gonna be balanced, and then I just did 5 to the, was not to, oh, I didn't, but it's just like 5 to the 10. Yeah, I did it wrong.
Yeah, that's what she's saying. Is like, I did it wrong, but she's got the right logic. Yeah. But see, this one on assessments, explain those ideas, right? So, yeah. All right, what are we thinking? Okay, so you rewrote it as an exponential. So what do you think the value of x is?
Figuring it, like on that one, we're just figuring out like what it should.
Wait a minute, guys.
Well, let me ask you this. What's 10 to the first?
I don't know how that came about, but.
It's just 10. What's 10 to the second? So,
Yeah, I just know.
it's how much?
Like I knew
100, right?
but I didn't know what I was doing.
What's 10 to the third? Yeah. So what is x? What is x? Okay. So my point is, one, keep in mind what a logarithm is, but man, just rewriting it as an exponential is actually way more useful because it's hard at first to think what a logarithm is, but if you think about what is the exponent, then it makes things easier. Okay. So let's bring it back. What's up? Yes, you can. All right, really quickly, so let's look at this. There's a couple of things that I want to point out. Again, I don't want to see you just type this into a calculator. I want to see understanding, because things like B, you cannot just type into the calculator, okay? So Leah, what did you do in part A here to help you figure out what x is?
Oh, you're talking to me?
Your name is Leah, yeah?
It's 20.
I really think like.
As in,
Yeah.
as what?
When?
Oh, 10. And then I didn't know what x was, so I just put an x and then I equaled it to 1,000.
At the end of the day, whether you write it this way or not, a logarithm is a what? Exponent. What's the exponent that goes on 10 to give me 1,000? 3. So what is x? 3. So don't forget, like, at the end of the day, if you are not super comfortable with the writing as a logarithm, you can rewrite it as an exponential and just find what the exponent is. The exponent is 3. But notice you can't always just do that, because when I look at b, how would I write that one? B. Or how could I figure out what b is? You just switched it around? How'd you write it? So 5 to the 5th power is equal to, well, what is it equal to though? Okay, so x equals 3,125, I believe. Okay. Now, one thing I want to pause and I want to point out here is this, because this is going to matter. So I'm going ahead and thinking about future lessons here. One thing that I could have done right here. What's the inverse of a logarithm? An exponential, isn't it?
Yes.
So could I have rewritten this as 5 raised to this power is equal to 5 raised to that power?
Huh?
So remember, you said the inverse of a logarithm is a what? Exponential. So hear me clearly on this. You didn't need this in this problem, but thinking about future lessons, this is why I'm applying this right here. It's an exponential. So I'm doing 5 and I'm making this my what? This is becoming the exponent. And whatever I do to one side of the equation, I do to the other. The reason I would want to do this is, what's the relationship between an exponential and a logarithm? They what? They cancel out. X is just equal to 5 to the 5th. I'm using the idea of inverses here to solve that equation. Does that change it at all? Same exact answer, right? In a similar way, when I look at C, what inverse would I use? Now this is odd. You don't usually see it written like this, but what inverse would I use? Huh?
Use x.
I would use x as my what? Base. So I do x
My bad.
raised to this logarithm equals x raised to the first. A lot of students mess this one up, but if you write it this way, oh, x is just equal to 9. That's it. Use those inverses. Or you can just do x to the first equals 9, either one. But logarithm at the end of the day is a what? I hope that we do not ever forget this. Davis, at the end of the day, a logarithm is a what? An exponent. Don't forget that.
Don't forget that.
I'm not going to stress about page 1, the next page. I want us to look at page 130 really quickly. Oh goodness, I'm glad I did not forget to record. Okay, so, way back in the day, now this is when I was teaching pre-cal, I actually used to have students do a mini research paper into logarithms. It helps students understand the history and understand what a logarithm is used for and why it's useful. But one of the big names that always came up with is this guy, John Napier. A long time ago, we never had calculators, we never had computers, things like that. And there are some properties that we're going to talk about tomorrow, hopefully. But there's some properties about logarithms that made working with astronomy and the sciences really easy, because it made really big numbers really small. And I want you to think about that. Like, we can already start to see this. The common log of, actually let's do this. 1 million is what? 10 to the 6th? Okay? Yeah, 10 to the 6th, okay? I want you to notice something really quickly. First off, these are inverses, aren't they? So the logarithm of 10 to the 6th is just going to equal what? 6. So the common log of 1 million is equal to just 6, right? The logarithm, the base 10 cancel out. So that took a really big number and made it really small. And when you're talking about sailing the seas and you're talking about astronomy, you're talking about thousands and millions of miles. So logarithms were useful there. In fact, they're still useful, we just don't have to do them in the same way. We have calculators to do a lot of the work, okay? But the two most frequent logarithms are the common logarithm, which is a base 10, and then the natural logarithm, which is a base e. The natural log is something you explore more heavily in algebra, or in pre-calculus, okay? So you do practice more with logarithms in pre-cal. But we're just going to focus on base 10, base 2, and base 3, I think. But be aware, natural logarithm, that's base e, legitimately shows up all over nature, right? So when you're dealing with logarithms in the natural world, usually a base e. The only thing I want to point out here is, really quickly, so this would be y equals 3 to the x right here. This would be y equals 2 to the x right here in purple. How do we know that this is y equals 2 to the x just glancing at it instead of 3 to the x? What should we notice about it? Not just that. Which one's growing more quickly? The blue, the 3 to the x, right? Because we're repeatedly multiplying by 3. Whereas here I'm only repeatedly multiplying by 2. So vertically, the higher the base, the quicker it grows, right? So notice right here, in the inverse, the higher the base, the more quickly it grows horizontally. I just want you to notice that small detail, that with the inverse function, the higher the base, the more quickly it grows horizontally. Does that make sense? Okay. So I just want you to see that quick, small relationship there. Not sweating that detail. Okay. Do want you to get some practice with this, so let's see. Oh, I think I might have skipped something out of the book. Maybe it's in a later lesson. So here's what I want you to do really quickly. Okay, so they don't have a space for a graph. What I want you to do quickly is this. For the last few minutes of class and tonight, before we continue tomorrow, what I need you to do is I need you to take a picture. So you can go ahead and get your phone, take a picture of this graph, and I need you to fill out the information on page, what page is this? 134, okay? So that's your only homework assignment. Identify those features on page 134. This is going to help you master these things. So this is essentially check your understanding. So please do this assignment tonight. No ands, if, buts about it. Do this assignment tonight.